Okay, well, thank you for coming on the very last day, and thanks for the invitation from Amir and Dr. Sen Gupta and others. I designed this talk to be an invitation rather than a talk, and the invitation is to an initiative that we've been pursuing at the Columbia Water Center called America's Water. And today I'm going to just talk about one segment of that initiative, which pertains to cities, because I took the title of the session on the built environment sort of narrowly. The initiative was launched about a year ago, and the way we've been structuring it is to bring in primarily the private sector together with universities to start thinking about future directions for infrastructure for water and for water technologies and engineering for the United States as a signal for what we should be able to do here that can then translate into dramatic improvements in the rest of the world. So that's sort of the motivation of this. And there's a number of people who've been working on this, so I haven't put all the names down. But the way I'm going to do this talk is first I'll give you a very quick and rapid snapshot of some of the key issues of the nation's water that motivate us, and then some of the directions that I see as possibilities for the future. So the first thing is this work that we have done on looking at water risk across the country, and this analysis is done by Naresh Devineni and others, and it focuses on looking at a daily time step. And the metric we use for water stress is the cumulative deficit between supply and demand accumulated at a daily time scale. So it captures multi-year droughts as well as seasonal variability, and we present it in different ways. For the purposes of this particular presentation, the key thing to note is that wherever you see reds, these are areas that have substantial overdrafts relative to their natural variability of water availability, not purely the mean value, but also accounting for major droughts. So where it is dark red, that means that you can have a cumulative deficit which exceeds 5 times the average annual rainfall availability in that area. So that's pretty significant. And obviously the Ogallala in California jump out, but what I wanted to draw your attention to is all the little red dots that show up in all the other areas. These are basically cities. So wherever you have a concentrated demand with a large city, beyond what we normally think of in terms of agriculture, we have an issue. Most of this issue is solved by either sucking up groundwater or by doing interbasin transfers, as is the case for New York City. So since the way I'm presenting this is the focus on variability rather than the mean value, one way we have buffered that is through dams, and we know that we haven't been building dams. In fact, we've been decommissioning dams. So we are increasing our vulnerability in line with the message one could get out of the last speaker, perhaps. The second is we've been depleting groundwater, and that particular graphic on the bottom right was developed by Tess Russo, who's here. And this is from an analysis of long time series from the US Geological Survey individual wells. And again, I would draw your attention to the East Coast, which many people think is well endowed with water, and you see many places where near big cities you're seeing these declines. The next big thread that comes out, which if you've been paying attention to the media, you probably know, and that's the aging infrastructure story for the United States. Water mains breaking at the rate of an average of 1,000 per day in the last several years. And the argument that comes up is that we need perhaps around $2 trillion over the next 30 or 40 years just to replace pipes, not for the rest of the infrastructure. If you add up the other infrastructure, we are talking around $3 trillion. So why are we looking at all these pipes failing? It's very interesting. Some of these were done 100 years ago, and their design life was 100 years. Some of these were done 50 years ago, and their design life was 50 years. So it all comes together very nicely for you. And this is like a spatial distribution of these things as estimated by people. And my point in bringing this up is the following. One of the arguments that you often hear with respect to radical changes in the US water infrastructure is, hey, we have a fantastic infrastructure with a significant sunk cost. Why would we change that? And what I'm saying is, hey, your sunk cost is just evaporating. In fact, you are looking at a major reinvestment in this infrastructure. So if the articulation by the ASCE and the industry is, hey, how are we going to replace this infrastructure? That's the wrong question. We really need to think about what should be our infrastructure and what should be the infrastructure for water for the 21st century globally. That's the opportunity. Now, financially, If you look at near-term things, this is based on an analysis done by interns at the Columbia Water Center, or looking at data for the last 12 years from water cost surveys, basically an analysis of the utility industry across the United States where these people have been responding. And two main things come up. Everybody's water rates have been going up. They were pitifully low, so maybe that's a good thing. But New York City has doubled, and that it's now at a fairly high number. In spite of that, the rate at which the debt for these utilities is increasing is double the rate at which rates are increasing. What that tells you is that maybe you should not be investing in municipal bonds associated with water utilities, because these people's ability to pay that off is questionable. So one of the things that happens to be living in New York is a lot of the municipal bond people start showing up and saying, can you tell us what the lay of the land is? And that's what motivated us to do this analysis. This slide here is from Alan Robertson, who's the Director of Federal Relations for American Water Works Association. And he points out that the other big thing that's coming up is that the EPA is coming up with a set of rules that's going to require a dramatic increase in what you have to remove from public water utilities before that water is supplied. So that cost is going to go up. And so the infrastructure costs that we have priced in of 3 to 4 trillion are actually not even close to what comes up if you bring this in. So summarizing all this, the question is, okay, we are looking at huge expenditures. We are looking at water stress. What should we be thinking about? And the argument I'm putting forward is we should be thinking about what I'm calling either a my water or a one water enterprise, where we switch from thinking from a supply side focus, which has historically driven our infrastructure, to a demand side focus. Who needs what? What do they use it for? What is the quality that is needed for that? What is the best way to provide it? And what level of redundancy do you have to build into the system so that you have the resilience and sustainability and risk management, but you also have much higher efficiency? And that, I think, would define also what a global water infrastructure direction should be. So that's basically the pitch. So let's look at some of these things. We have a model where we argue that because of economies of scale, we go for centralized systems for storage, treatment, distribution. And what's being shown is that these things have high energy intensity. They have high cost labor intensity, and hence those things may not really be translating into economies of scale in the same way when we funded this infrastructure from the federal government as centralized infrastructure. And today, that willingness to fund from the central governments or the federal governments is not nearly as much there, and the funding initiatives are likely to come from private venture capital, which may take a very different view of what they want to fund and what return on investment they would like to have. So if we want to think of the urban water system as a complete technological and use system, what I'm talking about there is that if you look at the institutional setting we have today, we have a drinking water utility, which is managed and operated quite separately from a stormwater disposal utility, which is to some extent managed integrally with a wastewater utility, but not always, okay? So again, this is all supply side services for all of those. And if you were to think about it from a decentralized system perspective, maybe not fully decentralized, but partially decentralized, then would you now think very differently about how you would organize those three functions? Imagine that you are one of these wonderful people who live in the West, which I used to do, and you want to be independent of the grid and you don't trust the federal government and the chemicals that they drop in your water. So you want your own integrated system. You might want to do rainwater harvesting, you might want to do groundwater, but you might want to recapture some of that in the waste that you generate as a use for different purposes for which different qualities might be there. So the idea is that instead of looking at some of the things that we look at as disposal problems, can we look at them as renewable resources? And indeed, Singapore has done that, and China and India are headed in that direction. We are starting to think about it, it seems like, but if the drought goes away, we stop thinking about it. So that's the idea. And then if you look through this stuff at the bottom line on this particular slide, the question that emerges is, well, we do have an institutional structure with water utilities, and if we start changing this, what would that business model change to? And then when I've talked to existing utilities in that context, United Water, which I'm going to slam because I was pissed off by their response, they said that we can't look at users starting to treat their own water because that would create a huge health hazard. Okay, so I'll jump to American Water, which are the good guys in my book. They're the largest private utility in the United States for water. Their response was, well, that we've been thinking about it, and we would change to a service industry where we would install, if there was point of use treatment and reuse, we would install sensors so that we have a much better assay on what is the water quality that the consumer is actually getting. We don't have that today. We have an assay of the water quality at the treatment plant, but not necessarily at the point of use. So even though you can talk about the health hazards that could come up, we need to actually do that. So they are investing heavily in sensor systems so that if you turn on your faucet, which is a drinking water faucet, it would go green, red, or yellow, depending on which chemicals you might be concerned about and what goes on. So the transformation then would come from the fact that American Water thinks that what they would do is they would do neighborhood sweeps with active sensors, where if there is a potential threat, they would sweep the whole neighborhood and change things rather than worrying about it at one level at a time. Okay, so let's look at our current infrastructure versus comparison. So the next 3 slides are from Dick Luthi at Stanford. They have a project called Renew It, which is one of the center projects from NSF. And he focuses on Southern California, which is where there's a lot of attention today. So the bars here show you the energy intensity and hence implied operation cost associated with different technologies. And what you see is that the recycled water is substantially cheaper than their current supply, which is substantially cheaper than desalination, which many of these people want to do. So how does that come about? It turns out that the water that is delivered from Northern to Southern California is pumped over 100 meters. Okay? Now, the energy intensity of desalination translates from reverse osmosis, translates to pumping at about 100 meters head equivalent. So in a way, whether you transfer from Northern to Southern California or you do desalination, in terms of energy intensity, that comes out to be about the same game. Whereas recycled water is about 1/3 of that energy intensity. Yet there's social acceptability issues and others that come up there. The other thing he points out is that suppose you wanted to expand those transfer systems, that's $1 million to $3 million a mile in terms of capital cost. So that's a fairly significant cost. Then they are looking at these distributed systems where there's potentially energy recovery from the solid waste or the organic waste that are created, but these are not centralized systems. These are distributed systems. And one of the arguments that comes up is that if you have a whole bunch of centralized systems that are connected, which basically is a decentralized or hybrid system, and the question is what's an appropriate scale for doing that, then if you have breaks or disruptions, these can be localized and you don't have larger scale cascading failures of that infrastructure. You also have much lower energy intensity costs and so on. So that seems like something that's interesting. So having brought that up, I'll give you one other example that I think is likely to be dramatically transformative or a disruptive technology, and that's the evolution of new membrane systems and new electrochemical treatment systems. A particular example I chose here is of graphene oxide or graphene hydroxyls. So these kind of filters are coming up now. They are at the nanoscale. They filter at 9 angstroms, so the water molecule goes through but nothing else. Okay? Now, one interesting thing about this technology that's shown on the bottom left graph is that the permeability of this membrane is about 100 times higher than the permeability of the membranes currently being used for reverse osmosis. So the interesting thing for me was, how does that happen? Okay, and it turns out that the material is relatively hydrophobic. So now what happens is, let's say you put a cylinder of water on top of this thin sheet of graphene hydroxide. It's hydrophobic. It can't repel the water upwards, so it repels it right through the pores. So you need very little energy to drive this. And obviously, we'll need pre-filtration. We'll need to deal with microbial fouling and other things like that. But think about it. If you take this, and this becomes the strategy for getting clean water out, whether we are looking at agricultural applications or others, if you can manufacture graphene oxide relatively inexpensively, then this is a breakthrough technology. And you could do this so that in your kitchen, you have this. In your shower, you have this, and you have maybe a robot that replaces it based on sensors. So you could dramatically change the urban landscape in terms of how you use these things. So that's the kind of thing that I'm bringing up. Now, the idea of reuse is not new. It's being, Namibia went to this about 30 years or 40, 50 years ago now. Big Spring, Texas went for this. So the public acceptability issues when you have stress start going away. And people are starting to implement these at the building and community scales, even in New York City. They're not using it for drinking at the end, but it's getting there. And this is without these disruptive technologies that I was talking about. So the key questions, and this is my last slide, that come up in terms of the way hydrologists should think about it is, we've been talking about ecosystem services and conservation of water. To get there, frankly, think about rainwater harvesting at the urban scale and reducing the load on the ecosystems. This is going to be a byproduct of trying to do some of these things. We'll have CSO reduction without talking about green infrastructure in novel ways. We will have a variety of these impacts that are positive. The question is public acceptance. Is your wife ready to believe, for instance, or your husband, that we can manage these kind of systems at home? That's the kind of question the utilities come up with. But that's also a new redesign story associated with this. Finally, one quick comment. I had a Chinese visiting student, and I had to do a calculation of if you had a 4-unit apartment with 4 residents in each apartment, and you wanted to do rainwater harvesting storage, as well as buy city water from New York City or Beijing, and also reverse osmosis treatment and storage, do me an optimization model with stochastic rainfall, and tell me, is this feasible? Beijing, answer is no, because of the monsoonal climate. In New York City, this comes out at 90 cents a cubic meter. And you do not buy city water most of the time. You have 70% reuse. I was rather surprised by that. But it turns out the New York City charges me $3.47 a cubic meter for the supply, most of which goes for wastewater treatment and stormwater disposal. So once you start thinking of that, you realize that this game is a game that can be played financially. Thank you.
You're a bit behind schedule, but maybe one quick question.
So the short answer is yes. Have we made a lot of progress on this yet? No.